Last time we introduced or reintroduced the concept of spin and talked about how very much it was like the orbital angular momentum quantity, or behaved in that way. One of the differences was that spin operated in its own spin space, whereas orbital angular momentum, L, can operate in regular XYZ configuration space, R theta phi, whatever. Today I want to do an example of putting, and we talked about particles with dipole moments. If I put them in a magnetic field, act like little compass needles. What I want to do is talk about what happens if I put a spin 1/2 particle at rest in a uniform magnetic field that points in the z direction. If that's the case, the Hamiltonian is going to be equal to the gyromagnetic ratio, alpha, times the magnetic field, times the component of the spin in the direction of the magnetic field. In this case, it's S sub z. That gives me minus gamma b naught h bar of 2 times the, of course, the S sub z, or the sigma sub z matrix, if you will, spinner. What we want to do then is to work out the eigenstates. They should be the same for the Hamiltonian as they are for S sub z. They should have the same eigenstates, so I can write chi plus with energy E plus should be minus gamma b naught h bar over 2. Chi minus with eigenvalue E minus should be equal to plus gamma b naught h bar over 2. And of course the energy is going to be lowest when the spin and the magnetic moment, or the field and the magnetic moment, point in the same direction, just like it's the case classically. The general solution to the Schrödinger time-dependent equation, I'm going to write as I h bar d chi dt is equal to h chi, is expressed in terms of stationary states, where chi of t would be equal to a chi plus e to the minus I e sub plus t over h bar, excuse me, plus b chi minus e to the plus I e minus t over h bar. And I can write this as a matrix A e to the I gamma b naught t over 2, b e to the minus I gamma b naught t over 2, where A and B are determined by the initial conditions of the system. In other words, chi of 0 would be equal to AB. And of course, normalize so that a squared plus b squared, it must be equal to 1. I'm going to write A as cosine alpha over 2, B as sine alpha over 2, such that then chi of t would be written as cosine alpha over 2 e to the I gamma b naught t over 2 sine alpha over 2 e to the minus I gamma b naught t over 2. And let's calculate the expectation value of S of x. I can write that as chi of t dagger Sx operator chi of t. If I put that into a matrix, I'm going to get Sx, if I multiply, if I take the Hermitian conjugate of this matrix, that changes e to the I to e to the minus I. This changes e to the minus I to e to the plus I. multiply those three together, I'm going to get, we'll do it quickly and simplify it, I'm going to get h bar over 2 sine alpha cosine gamma b naught times t. If I did the same thing for Sy, I would get, again, chi dagger T Sy chi of T. I would get minus h bar over 2 sine alpha sine gamma b naught T. And then finally, my expectation value for S sub z is chi dagger of T Sz chi of T. And that's going to turn out to be h bar over 2 cosine alpha. That tells me that my expectation value for S is tilted at an angle alpha to the z-axis and precesses about the field at a Larmor frequency. We call it the Larmor frequency equal, omega sub L is equal to gamma times b naught, again, where the gyromagnetic ratio is gamma. This is the same answer as we would get classically. And so this is a nice example of how to use spins in a constant magnetic field. Let's take this one step further. And the reason why I like to do that is because the whole experimental indication that we must take this other quantity that we call spin into account came about because of an experiment done by Stern and Gerlach. It's called the Stern-Gerlach experiment. The results of which indicated that these particles were not behaving as we would expect classical particles to behave. What they did, what Stern and Gerlach did was they shot a beam of silver ions, where of course the +1 valence is the thing that's going to be affected most by the magnetic field. But the magnetic field in this case was not a constant field, but it was a non-uniform magnetic field. It was an inhomogeneous magnetic field, so that there are going to be torques and forces on any magnetic dipole, like in this case the silver atom. And so we have a force that I can write as the gradient of energy, mu, or gradient potential, mu dot B. So this force is going to separate particles of a particular spin orientation. One spin will go one way, another spin will go another way. So picture a beam of heavy neutral atoms. As I say, Stern and Gerlach use silver, and they're traveling in the y direction. So the beam passes through a region of some static but inhomogeneous magnetic field. And maybe the field would be equal to something like this. Suppose I could write the field as a function of x, y, and z. And it may be minus alpha x I plus b naught plus alpha c k. So there's an inhomogeneous magnetic field. It's going to be, b naught would be strongest for the uniform field, and then you have a weak deviation from homogeneity with the alpha z component. So the force on the atoms, we would expect the force would be equal to gamma times alpha minus s sub x I plus s sub z k. Because of the Larmor precession about b naught, s sub x we would expect would oscillate rapidly and average out to 0. But there'd be a net force in the z direction. We might call that force, we'll call it f sub z, equal to gamma alpha s sub z. and it will make the beam deflect upwards or downwards in the z direction. Now, classically, we would expect there'd be a smear of these particles because S sub z wouldn't be quantized. But because of quantum mechanics, the particles are going to have their z component of spin quantized, and it's going to split into 2s plus 1 streams because angular momentum is going to be quantized. In the case of silver atoms, S is equal to 1/2, and therefore we have 2 beams. And that's exactly what was observed by Stern and Gerlach. And so this was the motivation to incorporate a quantum number, a quantity entity called spin. And as you see, it has made all the difference. One of the things that, probably one of the more complicated things that we can do. Now, by the way, you can read more extensively on the Stern-Gerlach experiment references like Townsend's book, which almost the first several chapters deal with spin and starts out with Stern-Gerlach machines. Fascinating treatment of spin, and I recommend it highly. It's a different point of view that we've taken in this course, although I've taught courses using that perspective. I recommend that Townsend's book quite highly, but it is different than what we're doing here. One topic that I'm a little bit hesitant to cover at the undergraduate level, but I almost feel like it's crucial that you be exposed to this, is what happens when we try to add an angular momentum. In other words, suppose we have 2 particles, and suppose they have spin 1 and spin 2 in 2 different states. So suppose I have particle 1 and particle 2. One is in the state S1, M1. Particle 2 is in the state S2, M2. And we wonder what happens if these guys interact. How's this going to? Well, we might say, well, the composite state of the system I could write as S1, S2, M1, M2, make a nice long ket, such that I could even write the quantities like this: S of 1 squared, S1, S2, M1, M2 should be equal to S1 plus 1 h bar squared times the big ket, M1, M2, and S1z applied to S1, S2, M1, M2 would be equal to M1 h bar, S1, S2, M1, M2, and similarly for the second particle, S2 squared applied to S1, S2, M1, M2 would be equal to S2 plus 1, h bar squared, S1, S2, M1, you're getting the idea here. And then finally, S2z applied to S1, S2, M1, M2 would be then M2 h bar, S1, S2, M1, M2. But we might ask ourselves, so we combine these guys, what is the total angular momentum? So in other words, what is the vector S, which we would say is equal to S1 plus S2? Well, let's start easier. Let's go with the Z component first. So I can write Sz of S1, S2, M1, M2 as just the sum. It would be SC of 1, S1, S2, M1, M2, plus SZ2, S1, S2, M1, 2. And I could write that as H bar M1 plus M2, S1, S2, M1, M2, which I could write then as H bar M, S1, S2, M1, M2, where M, we're just calling M1 plus M2. So M is just a simple sum. Great, but S is not so simple. Let's start as easy as possible, and then we'll get a little bit more complicated. We could get a whole lot more complicated, but we probably won't at this level. Let's take an electron in the ground state of hydrogen. We're going to try to make this really simple. So we just have an electron and a proton. Each has a spin, and that spin can be either up or down. So suppose they're both up. If they're both up, I get, for my quantum numbers, 1/2, 1/2, 1/2, 1/2, and of course m is equal to 1. I can have 1 up and 1 down, and that gives me 1/2, 1/2, 1/2, minus 1/2. That gives me m equals 0. I can have 1 down and 1 up. 1/2, 1/2, minus 1/2, 1/2, m equals 0. Then I can have them both spin down, which is going to give me 1/2, 1/2, minus 1/2, minus 1/2. And of course, and then would be equal to minus 1. It seems like we have one extra state where m is equal to 0. Because we expect with spin, m goes from minus s to s. So I should have minus 1, 0, and 1. I shouldn't have minus 1, 0, 0, and 1. It should only be 1 m equals 0. We better untangle this mess. Let's go over here and do that. Let's apply a lowering operator to the up case, the spin up case. So I'm going to apply s minus, which is s minus 1 plus s minus 2. I'm going to apply it to my spin up case. And that's going to be equal to spin minus of 1 up, times upcat plus my upcat times spin minus of 2 applied to my other upcat. Okay, I can write that as h bar. And you know what happens? This is going to turn this from up to a down. So I get h bar spin down, spin up, plus spin up h bar.
Could you speak up, Dr. Close?
Okay. That will give me h bar spin down, spin up, plus spin up, spin down, So I'm going to get, so 3 states with S equals 1 should be the 1, 1 state. Write it this way. Spin up, spin up. 1, 0 would give me 1 over square root 2, spin up, spin down, plus spin down, spin up. And 1 minus 1, which gives me spin down, spin down. That's my triplet combination. My singlet combination, 0, 0, would be 1 over square root of 2, spin up, spin down, minus spin down, spin up. So this is what we call my singlet state. This is my triplet state. The combination of 2 spin 1/2 particles can carry a total spin of either 1 or 0. And we can show, or it can be shown, that the singlet state is an eigenvector of S squared with eigenvalue 0. The triplet state is an eigenstate of S squared with eigenvalue 1 or minus 1. It turns out that through a great deal of algebra, you can combine spins of any type. In this case, we just took 2 spin 1/2 particles. You either get a spin 1 or spin 0, as we did. But we can combine 2 particles of any type spin with a great deal of effort and come up with a result. So for example, the highest total spin is going to occur when the spins are aligned parallel to one another, and the lowest will be when they're anti-parallel. So in this case, suppose I had a spin 2 particle, and I combine it with a spin 3/2 particle. So my possibilities, of course, the highest would be 7/2, and then I could also have 5/2, 3/2, and 1/2. On the other hand, to make a more general statement about this, we can write a combined state as a sum over m's, m1 plus m2 equal to m, c sub m1, m2, and m, s1, s2, applied to S1, S2, M1, M2, where C is what we call a Clebsch-Gordan coefficient. There are tables, in fact there's one in your text, of Clebsch-Gordan coefficients, and you can use them to calculate the result of combining 2 or more systems of spins. And using those tables, it is a bit complicated. It's probably more than I want to do at this level, but you can use that table to come up with the coefficients, which will give you the result of the addition of spins for 2 particles. You'll see more about this at the graduate level. All of this is based upon applied group theory. And you can, as I say, use the table in your text or in other references to calculate what the sum would be, or the possibilities would be, for combining 2 spin systems together. you may see more of this, as I say, at the graduate level. Let me stop with that today, and we'll save for next time, we'll talk about some electromagnetic interactions. Some of them one of them I'm sure are extremely surprising. Thank you.